The German engineer let his palm glide along the Sherman's glacis, as if the steel might confess something under his touch. He had been told this American tank was crude, an overgrown tractor wrapped in thin plate, churned out by a country that had never truly learned the language of armored war. Yet the first thing his fingers found was not clumsiness, but precision. The weld beads were not lumpy scars from hurried work. They were smooth, consistent, almost identical from seam to seam, clean enough to look machine-laid. The kind of uniformity you only got when a factory's rhythm was so practiced, it became a kind of certainty. It was April 1943, and the tank sat under guarded scrutiny at Kummersdorf, the Reich's premier proving ground south of Berlin. 2 months earlier, in Tunisia, German recovery teams had seized it, serial number USA 3067641, an American medium tank the Germans had dragged out of the desert like a trophy. The Lieber Americans, according to the paperwork and rumor that followed the vehicle like a shadow, had called it War Daddy 2. High Command wanted it peeled open like a watch, every weakness diagrammed, every vulnerable plate assigned a firing solution. They wanted a report that would make them smile. The engineer had spent 3 weeks living inside the Sherman's silhouette. He measured, tapped, listened, and disassembled. And the longer he stayed with it, the more unsettled he became. Not because the tank was invincible, but because it didn't behave like what German intelligence had promised. The terror wasn't in the armor thickness or the gun size. The terror was in the method. Germany, he realized, was still crafting war machines like masterpieces. America was turning them out like printed pages. War Daddy 2 had been captured on February 22, 1943, in the aftermath of the fighting around the passes and ridgelines that would stain American memory. 8 days after the Battle of Sidi began, the U.S. 1st Armored Division had been battered by German panzers, driven backward toward Kasserine Pass, stumbling through chaos that no report could fully translate. The Sherman belonged to Company G, 3rd Battalion, 1st Armored Regiment. In the confusion of retreat, its crew abandoned it. Maybe fuel ran dry. Maybe a track was damaged. Maybe a hit crippled mobility without killing the vehicle. The records were silent on the moment it was left behind. But the records were not silent about what happened next. German recovery teams found the tank intact, and unlike most captured vehicles, it did not need coaxing or miracle repairs. They climbed inside, turned the controls, and it started on the first try. That single detail should have been written in red ink. They drove the Sherman more than 200 miles across desert distances to Tunis over 4.5 days. No breakdowns, no mysterious failures, no final drives shattering on a whim. It just kept moving, a steady mechanical animal that didn't seem to care whose hands were on the levers. From Tunis, it went by ship to Germany, delivered not to a frontline unit for propaganda photographs, but to engineers with calipers, notebooks, and the Reich's highest expectations of superiority. Kummersdorf had evaluated captured Soviet T-34s back in 1941. Those examinations had shaped the thinking that birthed the Panther. Now, at last, they had an American medium tank to dissect. The mood when the Sherman arrived was almost theatrical. German intelligence had dismissed it as a mass-produced compromise. Thin armor, a mediocre gun, a cheap design from an industrial nation that, in the German imagination, didn't understand refined mechanics the way Europe did. The engineers approached it like artisans inspecting a counterfeit, ready to sneer at sloppy welds, brittle steel, crude fitment. Several had pens poised for a scathing assessment that would reinforce the comfortable belief that German engineering remained unmatched. They began with the armor. They measured every plate, calculated angles, and stenciled figures onto the hull in white paint like a surgeon marking a patient. The thickness was adequate, nothing more. About 51 millimeters at the front hull, around 38 on the sides. A tiger could punch through that at long range. On paper, the armor did not inspire fear. Then they opened the engine compartment, and the mood shifted. There, sitting in the rear like an aircraft heart transplanted into a ground vehicle, was the Continental R975 radial engine. It looked exactly like what it was, an aviation power plant, adapted for armored use. 400 horsepower, air-cooled, designed to be dependable in conditions where mechanics might not easily reach it. The engineers immediately ran the numbers. A Sherman weighed around 30 tons, producing roughly 13 horsepower per ton. Oh, Panther weighed about 45 tons with a 700 horsepower engine, about 15.5 horsepower per ton. Only slightly better, despite the Panther's much greater weight. But power wasn't what made the Germans uneasy. Any nation could build horsepower if it devoted enough resources. What shook them was access. The Sherman was built like the Americans assumed the worst. That field maintenance would be done in mud, under fire, by exhausted men with basic training. Large hatches allowed mechanics to reach major components. Routine servicing was straightforward. Oil changes were fast. Spark plug access was practical. The design didn't demand genius. It demanded competence, and it rewarded it with reliability. German engines did not forgive so easily. The Maybach HL-230 in the Panther was powerful, yes, but it was sensitive, demanding, and plagued by cooling issues that could cascade into fires. Routine maintenance often required factory-trained specialists. Removing or replacing the engine could require a crane and consume a full day even in controlled conditions. Where the Americans built a tank that could be serviced by almost anyone in the field, the Germans built tanks that too often had to be sent back to factories like injured racehorses. The engineer kept turning pages in his notebook, and the notes felt less like criticism and more like warnings. Then came the sound, or rather, the absence of the sound the German engineers expected. When they ran the drivetrain, they were accustomed to the high-pitched whine of spur gears, straight-cut teeth fighting friction under load. German transmissions screamed because the geometry demanded it. The Sherman, when pushed through its powertrain tests, did not scream. It hummed. One engineer called others over, as if the tank were performing a trick. The Americans had used herringbone gears, precision-cut, helical teeth that meshed smoothly and distributed load in a way that reduced wear. This was not merely a nice feature. It was a declaration of industrial capability. Herringbone gears demanded complex machining and specialized cutting tools. They demanded time and materials. German tanks often relied on spur gears because they were quicker to manufacture and required less sophisticated tooling. Even that compromise had reasons. Germany's access to tungsten carbide and other strategic resources had been squeezed by blockade pressures, and the tooling required for advanced gear cutting wore out faster without those materials. So Germany reverted to simpler solutions. The Sherman's transmission, by contrast, promised longevity, thousands of miles before overhaul. German engineers had seen Panther final drives fail with alarming frequency. In the field, the average lifespan could be shockingly low, sometimes measured not in years or even months, but in a handful of hard marches. The engineer at Kummersdorf stared at his measurements and felt the floor shift under him. A Sherman could travel from Normandy to Berlin under its own power. A Panther might struggle to survive the journey from railhead to front line. Every comparison felt like salt. In a wound, the Reich refused to admit it had. They documented the gear geometry, the machining quality, the tolerances. They tried to translate it into German manufacturing terms to ask the practical question: could the Reich do this at scale? The answers kept coming back as variations of no. No, not quickly. No, not with current tooling. No, not with materials increasingly scarce. No, not with factories organized around hand-fitting craftsmanship rather than interchangeable mass assembly. And still, the most unsettling surprise had not yet revealed itself. When they inspected the gun mount, they noticed a small box attached near the 75mm gun's installation. Cables ran from it toward the gunner's position, terminating in a gyroscopic assembly and related components: a gun stabilizer. A stabilizer in an American mass-produced tank. Not an experimental prototype, not a luxury modification, an integrated system. The Germans had experimented with stabilization concepts. They understood the theory. What they struggled with was miniaturization and precision. This American system, associated with Westinghouse, was not perfect. It stabilized primarily in the vertical plane, and it did not create modern shoot-on-the-move accuracy the way later systems would. But it achieved something operationally devastating. It kept the gun roughly aligned while the tank moved, allowing the gunner to acquire and fire quickly after halting. German tanks often needed 10 to 15 seconds for suspension movement to settle and for the gunner to properly re-aim after stopping. In a duel, those seconds were not seconds, they were life. The first accurate shot frequently decided the engagement. With a stabilizer, the Sherman could stop and deliver its first aimed round faster than a German crew could fully recover from its own vehicle's bounce. The engineer examined the gyroscope, the servo mechanisms, the cabling, and the mounting. He tried, instinctively, to imagine German factories replicating it. He imagined the precision electronics, the clean manufacturing, the dependable wiring. He imagined the copper, the materials, the production time. Then he stopped imagining, because the reality was grim. They could not replicate it, not in time, not in numbers, not with an industrial base already stretched and stressed, not while bombers tightened the noose and blockades constricted supply, not while German production culture remained tied to artisan perfection and ideological pride. Yet High Command did not want philosophy. They wanted spectacle. In June 1943, War Daddy II was transferred to Hillersleben for a demonstration. The generals did not come to watch a quiet reliability test. They came for a show that would confirm what they already believed. Senior officers and decision-makers gathered, men who influenced production priorities, men who could steer resources toward Tigers and Panthers, or, in theory, toward something else if the evidence forced their hand. The test organizers chose a dramatic challenge, a steep slope of loose sand, around 30 degrees, where traction and torque could be made to look like destiny. The Panther went first. It roared up the hill with the confidence of a predator. Its wide tracks bit into the sand. Its engine did not hesitate. It made the climb look effortless, like a demonstration meant for posters. The officers smiled and exchanged satisfied looks. This was what German superiority looked like: power, grip, performance. Then came the Sherman. War Daddy II rolled forward on narrower rubber block tracks designed for road marches and practical movement. As it met the loose sandy incline, the tracks slipped and spun. The engine strained. The vehicle, clawed for purchase, then slid backward, defeated by a test chosen to highlight exactly this kind of weakness. The Sherman failed the hill climb. The generals applauded. They believed the demonstration had proven what they wanted proven. The engineers did not applaud. To them, the Sherman's failure on that slope was not a victory for German design. It was a warning about German thinking. The Panther had won a sprint, but the engineers knew, with a kind of cold certainty, that the Panther might not survive a marathon. The Sherman had already performed the feat that mattered most. It had driven over 200 miles across Tunisia after capture without collapsing into mechanical failure. It had reached the demonstration site by existing as itself, by being a tank that could reliably arrive. The Panther's climb was impressive, yes, but it did not erase the fragility the engineers had seen in German final drives and maintenance demands. The hill climb validated the wrong instincts. It convinced the military leadership to keep building high-performance thoroughbreds rather than dependable workhorses. The men who had spent weeks inside the Sherman's compartments understood the deeper truth, but they watched their superiors cheer a controlled failure and walk away satisfied. Nobody wanted to hear that the American tank's inability to climb a specific sandy incline mattered less than its ability to cross entire countries and still start when asked. Then Albert Speer came to see it for himself. Speer, the Reich Minister of Armaments, stood at the intersection of ideology and production. Every tank, aircraft, and submarine flowed, in one way or another, through his authority. He had a reputation for efficiency and had increased weapons output through reorganization and streamlining. He believed German engineering, properly managed, could outproduce the Allies, or at least narrow the gap. Photographs exist of him examining War Daddy 2, studying its lines with the expression of a man searching for a lever he could pull. He reviewed reports, spoke with engineers, and formed a conclusion that would follow him long after the war. Later, in Memoir and Reflection, Speer noted reports from Italy praising the Sherman's mobility and cross-country performance, the way American armored units could traverse terrain German experts considered difficult for heavy armor. The Sherman's power-to-weight ratio contributed to real mobility, but Speer saw beyond any single performance metric. He recognized the structural problem, the kind that cannot be solved by one brilliant redesign. Germany was building complex machines that often required rail networks and careful logistical planning to move and sustain. America was building a mobile force that could, to a frightening degree, drive itself to the battlefield, be maintained there, and keep going. The Sherman was not just a tank. It was an industrial philosophy made metal. American design. Priorities were brutally practical. Reliability, maintainability, mass production. American engineers accepted compromises because those compromises served the system. A less powerful gun could still win if it was dependable and had plentiful ammunition. Thinner armor could be justified if it reduced weight and increased mobility. A simpler design mattered because it meant faster production and easier field repair. The Americans built for the way war actually worked. Mud, distance, supply lines, exhausted crews, constant movement. German industry, by contrast, prioritized technical superiority, precision, capability, performance. It produced marvels, tigers and panthers that could dominate a battlefield when they ran properly. But the war was not a laboratory duel, and superiority on paper did not guarantee availability on the road. German engineers were brilliant, but their brilliance had been aimed at the wrong target. They optimized for excellence in the individual machine, while the Americans optimized for excellence in the system. The men who understood this most viscerally were not ministers or designers. They were the crews who lived and died inside steel. Alfred Rubbel, a Tiger commander in a heavy tank unit, who would later be credited with dozens of kills, had first-hand knowledge of what German armor could do, and what it could not do, especially outside combat. His unit used captured Shermans for recovery and supply duties. He compared the American tank to a reliable civilian car. You pushed a button and it started. With a Tiger, there was always a procedure, always a ritual of checking fluids, warming systems, worrying about transmissions. German crews loved their Tigers and Panthers when those tanks worked. The problem was how often they didn't. By 1944, reports from German armored divisions spoke of operational readiness, hovering around a third to less than half. That meant more than half the vehicles were unavailable at any given time, broken down, awaiting parts, immobilized by maintenance demands or mechanical failures. American armored units, in contrast, maintained readiness that could exceed 85%. When American commanders needed tanks, they had tanks that ran. When German commanders needed tanks, they sometimes had impressive machines sitting silent, waiting for components that might never arrive. Numbers have a way of stripping propaganda bare. And then Normandy arrived, and the Kummersdorf engineers' fears became visible in smoke on French roads. During the retreat from Normandy, many Panthers were abandoned and destroyed by their own crews, not because enemy shells had shattered them, but because mechanical failure had turned them into burdens. Imagine the frustration. Possessing the thickest armor, the most dangerous gun, the reputation of supremacy, and standing by a roadside watching your transmission fail while columns of inferior Shermans rumbled past, still moving, still arriving, still fighting. They did not lose only because they were outshot. They lost because they often could not reach the fight. During the Battle of the Bulge later in the war, the situation grew worse. By late 1944, a significant portion of German heavy tank losses were tied to non-combat causes, breakdowns, fuel shortages, immobilizations that left vehicles to be abandoned or destroyed. American gunfire mattered, of course, but it did not have to do all the work. The German armored force was bleeding itself dry through the friction of its own complexity. Back in April 1943, the engineers at Kummersdorf had seen the future in the Sherman's internals. They had tried to look past the hill climb spectacle and focus on what actually decided wars: the brutal mathematics of reliability, the relentless advantage of maintainable design, the industrial capacity to replace losses quickly and keep machines in motion. They documented American advantages and wrote reports explaining why mass production and dependable logistics would grind German excellence into defeat. But the generals had watched the Sherman slide backward on loose sand and walked away satisfied, convinced that German engineering remained superior. Germany could not simply adopt the American manufacturing philosophy, even if it wanted to. The constraints ran deeper than pride. Strategic materials were scarce. Complex tooling required resources Germany increasingly lacked. Precision electronics demanded copper and other materials strained by blockade and bombing. Factory culture could not transform overnight. German industry relied on skilled craftsmen and hand-fitted components. American production relied on interchangeable parts, assembly lines, and procedures designed to scale. Converting one system into the other would take time Germany did not have, and ideology made the transition even harder. The regime's belief in inherent technical superiority was not just propaganda, it was a worldview. To admit that American mass production techniques were better in practice was to admit a failure at the level of identity and doctrine. So the Reich stayed the course. It kept producing magnificent machines that too often spent their lives waiting for repairs rather than shaping battles. America, meanwhile, kept printing tanks,